Okay, so it's 8 o'clock. It's time to get started with our lecture. So please turn off your computer screens and computers, and let's get started. If you are not here on Monday, you should have everything you need for the course, the syllabus, the first lecture slides, and the first homework available on tracks. So you can go to the web and find the track site for this course, and you should be able to access the syllabus, the first day PowerPoint slides, and also the homework. You have a homework due today. If you were not here on Monday, you have till today, this afternoon, to submit that homework. So it's something that you can finish in 5 minutes. So you can go to my office and by this afternoon and submit it. So if you have your homework with you, I'm going to be passing around now to collect it. Also, there's a assignment sheet. So if you that should be in another room. Yeah. You turn up the I think I didn't mention that last time. You're not going to be evaluated based on attendance, but I used that assignment sheet for data collection purposes. I'd like to see how if there's any correlation between the attendance in class and the performance of the students in the course. So I really encourage you to come to class. Based on my previous observations, there's a high correlation between students who come to class every day and the performance in terms of doing well in the course. Any questions? Yes, sir.
Why would you follow along slides?
It's going to be the same information.
It's easier.
Okay, so you can follow. If you're going to be watching or looking at the slides, I'll let you try it, but if I see that everybody is getting distracted with the computer, I will stop allowing you to look at the monitors. But one thing I need to mention is that you need to have, it will be good to have a hard copy of the slides, because you have to make notes on those slides while I'm teaching. So you'll see why. Any other questions? Okay, so today we're gonna have our first discussion topic, which is product, process, and schedule design. And this is material that is part of your chapter number 2 in your textbook. So I always like to start the lectures reminding you the objectives for this course. So these are the 3 things that you need to master once we finish the semester. So understand the principles of facility location, layout, material handling systems, and to practice designing facilities. Learn formulation models and analytical procedures for the study of facility layout planning. And learn the fundamentals about material handling and be able to design layouts incorporating product, process, and personal requirements. So as you can see, our topic today is very related to that 4 objective. So the agenda for today, we're going to go over these 4 major topics, product design, process design, schedule design, and facilities design. Might not be able to get to the last one, so that might be something that we will continue on in our next lecture. But in terms of the objectives for this lecture, we have to learn the product, process, and schedule design functions. So we're going to use this PP&S to abbreviate these three words. So if you see this, that means product, process, and schedule, as they relate to facilities planning and understanding the interactions between facilities planning and the product, process, and schedule design. So let's start with the product design. So the product design involves two things. The first one is to decide which products are to be produced, and the second one is the detailed design of individual products. Okay, so these two things are related to the product design, and I'm showing here one CAD design for a cell phone. So we're going to talk about that later. Decisions regarding the products to be produced are generally made by upper level management. And if you took project management from me or from Dr. Jimenez, we talk about this in detail in that course. Why are these decisions made by upper level management, and how are they involved in this decision making? The design of a product is influenced by several things. First one, aesthetics. Second one, functions, materials, and manufacturing. So when you're planning the design of this product, you have to take into consideration all these things. That will influence how the product is produced, and also can also influence how many units are you going to sell. If you are able to provide a good design in terms of aesthetics of your product, that will be easier for you to market, for instance, and so on. So marketing, purchasing, industrial engineering, manufacturing engineering, product engineering, and quality control, among other factors, will influence the design of a product. So I want you to keep in mind what we are trying to do. We're going to be building from the building blocks up to the top level. So we want to show you how the product design, how the process design, and the schedule design affects the facilities planning. So in terms of product design, we can use pictorial representations, and prototypes as inputs for the facilities planner. So here is an example of a drawing or a pictorial representation of a particular assembly. So as you can see, it's very detailed in terms of the part numbers that are needed for to get that particular product completed, and also the picture shows you how the product needs to be assembled. Okay, so these are some of the tools that we can use. Also, photographs and drawings allow the planner to visualize how the product is to be assembled. So if you are would like to see how the product itself is going to look in reality, you can also produce this type of picture for helping in the assembly of the product. But as you can see, we have multiple components in order to put together this whole assembly. So detailed component part drawings are needed for each component part. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, around 10 different components. So we also needed specific design or draw for each one of those components. The drawing should provide part specification, and dimensions in sufficient detail to allow part fabrication. So one of the decisions that you have to make as a facilities planner is you saw that for this particular assembly you have 10 components. You might be able to produce some of them, you might be able to produce all of them, but sometimes you have to make decisions in terms if it's better for you to buy some of those components or if it's better for you to manufacture those components. So we're going to talk about those details later in this lecture. So just keep that in mind. The combination of exploded assembly drawings and component part drawings fully documents the design of the product. And any idea how can you create this type of diagram? I don't know if any of you have any experience designing or creating these diagrams using a computer. Yeah, I guess so, right? Because you take one course at the beginning of your degree, teach you how to use a CAD software. So the drawings can be prepared and analyzed with a computer aid design software. And when I was an undergrad student, we used AutoCAD. I don't know if that's what you're still using. So you can use AutoCAD to create these components. Concurrent engineering can be used to improve the relationship between the function of a component or product and its cost. So we talked a little bit briefly about concurrent engineering in our first lecture. So basically what you're trying to do, instead of follow a sequence of steps, you're trying to combine some of them so you can come up with a better design of your product. So functions are integrated to reduce the elapsed time required to bring a new product to market. And concurrent engineering provides a simultaneous consideration in the design phase of life cycle factors such as product, design, materials, manufacturing processes, testability, serviceability, and quality and reliability. So as you can see at this point, in this course, you're going to be listening about different things that you have already taken as part of your program. So some of them, manufacturing processes, quality and reliability, because all these things relate to what you're trying to achieve, which is designing a new product, new process, finally a facility. So any questions so far? Okay. So let's talk about, we talk about product design. Now we're going to transition to process design. So in process design, we're going to determine how the product is going to be produced. So you have your product already, you have the idea of the product that you want to take to market. Now you have to design the process to take that product from an idea to a real product. So you have to decide whether, as we mentioned, we're going to have multiple components. So we need to decide whether the part will be purchased or produced. And we're going to take into consideration multiple things. One of them is going to be the cost, but also you have to take into account the time for delivery. If it's going to take a long time even though if it's cheaper, it's going to take a long time for you to receive that component, then it might be better for you to pay a little more to get the component on a timely fashion. Okay, so there's going to be multiple things to take into account. So for parts that are going to be produced, the process designer must determine how the part will be produced, second, which equipment will be used, and finally, how long it will take to perform the operation. Okay, so you need to take into account how the part is going to be produced. These are for the once you make the decision that this is something that you want to manufacture in your own plant. How are you going to produce that one? Which equipment you need to produce that particular product or component, and how long is it going to take for you to complete that process. So the final process design is depending on both the product and the schedule designs. So in our next slide, these are some of the tools that you can use to decide whether you want to produce or buy a particular component for your process or for your final product. So here's the make or buy decision process. So this is a list of questions that you can follow in order to decide whether you should buy or manufacture a particular component of your product. So if you follow the flow chart, first question is, can the item be purchased? If the answer is no, then there's nothing else to decide, then you're forced to produce that particular component. But if you can buy that component, then you can follow the flow chart can we make that item? Do we have the equipment? Do we have the raw materials? Is it easy for us to get those raw materials in order to produce that component, and so on? If the answer is no, then you should buy the component. But if the answer is yes, then you think about the cost. Is it cheaper for us to make than to buy? If the answer is no, then you buy. If the answer is yes, then you're going to look at the resources that you have available. So if the capital available allowing us to, so the money that you have available in your department will allow you to produce that component. If the answer is no, then you buy. If the answer is yes, then after answering yes to all the questions, then you decide to make the component in your own company. Okay? So these decisions will require the input from this area of your company, so finance, industrial engineering, marketing, process engineering, purchasing, human resources, among others. And you can see why, because you're going to be affecting, let's say you only have 10 employees working in your area, you're trying to bring a new process into your area, that will require more employees. So if you're not able to hire more people, which is a human resource decision, then you might not be able to produce that particular component in your company. So that's how all these areas, and for sure if you hire more people, you're going to be affecting finance and other areas, maybe purchasing for the hiring of these new employees. So all these areas are related to these decisions. Okay, so any questions? So one more time, we have split them from product design, process design, and then we're going to move to schedule design, and we're going to see how everything affects the facility design. So the next thing that I have here is called part list. So the input to the facilities planning or planner is a listing of the items to be made and the items to be purchased. So once you have decided which components of this final assembly are going to be purchased and which ones are you going to be making in your own facility, then you have to provide that list to the facilities planner. Okay, so here we have an example of a part list for an airflow regulator. So we have the part number, and that follows the part name. We have also listed the number of the drawing. So if you want to reference the design of that component, the number of units that are required for that assembly, the material, the dimensions, and the decision in terms if you're going to buy or make that in your facility. So that last column is the decision on whether you're going to make or buy that component. Okay? So the listing of take the form of a part list, or a bill of materials. And on the next slide, I'm going to show you how a bill of material looks like. So a bill of materials is often referred to as a structured part list and contains the same information as the previous document, the part list, plus information of the structure of the product. So that basically refers to this first column, which essentially is telling you the level in terms of how to build the component from the basic blocks up to the final assembly. So level 0 is the basic level. You go level up, you require some components to assembly that level, and so on. So typically, the product structure is a hierarchy. So referring to the level of product assembly. So level 0 usually is the final product. Level 1 applies to subassemblies. And components. And level 2 refers to the subassemblies, components as they feed the first level, and so on. So I think I told you the opposite on the previous slide. We go back to this. So level 0 is the final assembly. Okay? So this is usually represented as a single line. So if we go back here, that should be only one line. That's your final assembly. Level 1 contains some of the sub-assemblies. So if you see this one is by itself right here, that might be because that's an assembly that is purchased from a supplier. But here you see how this main assembly contains multiple components at different levels. Any questions? And I think you have seen this in some of your courses already, maybe for production planning. But as I mentioned, all those ideas, the ideas discussed in previous courses are going to be reflected here because we need all that information to design our facility. So once a determination has been made concerning the products to be made in-house, then decisions are needed as how the product will be made. So we already made the decisions in terms of which parts are going to be purchased, which parts are going to be manufactured. Now we need to decide how are we going to assembly or produce this final product. So the process selection procedure involves the following steps. First one, define the elemental operations. Identify alternative processes for each operation. So you might have multiple ways to produce a particular part. And for example, when I was working for Johnson & Johnson, we have a manufacturing line to produce a certain type of Tylenol. But we designed a new process that will cut the space requirement for that final manufacturing line to the half. So we were experimenting with that in a different area. So and actually we were able to produce the same product with the same quality. So that means that you can change that production line requiring less space from your production facility. So there might be always different ways to process a particular operation. And this final decision is made based on the components that we already discussed. So we're going to analyze the alternative processes. And once we decide which are the processes that we're going to use, we need to standardize the process. Finally, evaluate the alternative processes and the last step is the final decision about the selection. Okay, so one more time, you might have different ways of producing that component. You will look at the alternative. You're going to make that decisions based on your financial ability to pursue some of them, the resources that you have available, number of employees, and so on. And the space might be another thing, time, and so on. So in terms of selecting the required processes, the facilities planner will not perform process selection. That's not a decision made by the facilities planner, but an understanding of the overall procedure provides the foundation for the facilities plan. So once that information is provided and you have a good understanding of that information, then you can start planning for the facility. Step 1 of the procedure involves the determination of the operations required to produce each component. And in order to make this determination, alternative forms of raw materials and types of elemental operations must be considered. The second steps involve the identification of various equipment types, capable of performing elemental operations. So this not necessarily means that you need to buy new equipment. If you have an area of your facility that's underutilized, you can always use those resources, or you might try to use those resources to be part of this new process. Manual, mechanized, and automated alternatives should be considered. Okay, so one more time, the facilities planner will not make process selection, but we need to have a good understanding of the overall procedure. That's the foundation of the facilities plan. So step number 3 includes the determination of unit production times, and equipment utilization. For various operations and alternative equipment types. Okay, so the utilization are inputs into step 4 of the procedure. Step 5 involves the economic evaluation of alternative equipment types. So another course from your degree showing up here, economic evaluation, economic analysis, the use of net present value, the use of different type of analysis to make the decision at time 0. So the results of the economic evaluations are the basis for the final step, which is step 6. Okay, so as you can see, this involves a lot of things. The output from the process selection procedure are the processes, equipment, and raw materials required for the in-house production of products. And the output is given in the form of a route sheet. And I'm going to show you a route sheet on the next slide. But in order to prepare this diagram, you need to have some data. So what I'm showing you in this table is the data that you will need to create this route sheet. So these are the route sheet data requirements: component name and number, operation description and number, and the operation may include shape, drill, cutoff, and so on. Equipment requirements, so what type of machine are you requiring for that particular product. Unit times, so if you need to prepare the machines in order to produce that particular component, do we have a setup time? Do we have a maintenance time? How long is it going to take to complete each unit? And finally, the raw materials requirement. So one example that I always think about when I see these raw material requirements is in the the production of motherboards for computers. If you look at these machines, they produce a lot of these boards really quick. You can say 1,000 in less than an hour. But they require a lot of maintenance in terms of changing the rolls that contains the components. So you have to be aware of how many of the rolls you need per hour, and you make sure that you have those ready for input. Okay, any questions? So we're still talking about process design. We talk about the requirements for the route sheet. And on the next slide, we have an example of a route sheet. So this is to produce an airflow regulator. So we have on the first column the operation number. So we have a number that basically will identify that operation, the description of the operation, and the type of machine that you're going to use. In terms of the tooling, this provides some information about the machines and the equipment that you're going to be using, the setup time for that particular operation, the operation time in terms of hours, and the materials that you are needing for each one of the operations. So this again, one more time, this is standard forms that are used in manufacturing and production. This is called a route sheet. Now, another diagram that provides a lot of information and is very simple to create is called an assembly chart, which provides the method of assembling the product. And by looking at it, you get the idea of how this product is going to be assembled. So let me show you some of the details from this. So this SA stands for subassembly. Then A is assembly, and we use circles. And then we have one more symbol here, which is a square, and that I, any idea of what that means? I? Say that again?
Inspection.
That's correct. That's an inspection. So before we get to the final assembly, we do an inspection of the subassembly that's coming from this area. So we have a subassembly containing all these components. We provide that assembly 2 and assembly 3, an inspection, and a final product. So the easiest method to constructing an assembly chart is to begin with the completed product and to trace the product, this assembly, back to its basic components. Okay, so you do a backward process to get this done. An assembly chart does not provide the overall understanding of the flow within the facility, but by superimposing the road sheet and the assembly chart, a chart result that does give an overview of the flow, which is called the operation process chart. And the reason that I'm showing this picture here is to give you an idea of all the things that are involved: facilities, assemblies of assemblies, raw materials, and so on, in order to produce a tire. So you start with the raw materials: rubber, textile, chemical things, and so on. And you start putting them, taking them to different facilities, and then assembling them together until you get the final product. So something that's, you might think that is a simple product to produce, like a tire, involve a lot of things, and we need to plan for those processes in order to get this product done. So going back to the diagrams, so we have one called the route sheet, we have another one called the assembly chart. So what we are saying is the assembly chart is not giving you information about the flow within the facility, but we can use the route sheet in combination with the assembly chart, and we can come up with a new type of chart that will provide you with the information about the flow. And that chart is called the operation process chart. And that is right here. So now we have more information about the product. We have information about the type of operation that you're going to be producing, and you know the flow in terms of getting the final assembly completed. Okay, so going back, this is combining the assembly chart with the route sheet. So to construct this operation process chart, we begin with at the upper right side of the chart with the components included in the first assembly operation. And if the components are purchased, they should be shown as fitting horizontally into the appropriate assembly operation. So that'll be the products showing up in the horizontal position. So these are those: plumber retainer, these tip ring plunger, and so on. If the components are manufactured, they should be shown as fitting vertically into the appropriate assembly operation. And the operation process chart may be completed by continuing in this manner through all the required steps. The product is ready for release to the warehouse. So if you took, and again I'm going to be talking about all these courses. Let me know if you haven't taken any of one of these courses already. If you took operation research, we talk about neck flow charts, how to construct a network and how to use a network to find a solution to a problem. We can use also those concepts to design a new type of graph, second viewpoint, based on graph and network theory, is to interpret the chart as network representations. So when I talk about a network, this is what I'm talking about. So it's a graph that looks like this. You have some arcs and some nodes, and you can find let's say if you're looking at the shortest path, you can find the shortest way to go from one node to the other, and so on. So that's network representation. The precedence diagram is a directed network and is often used in project planning. Okay, so I'll give a bonus point to anyone who can tell me what is a directed graph. And that's gonna be for the first exam. Anyone remember what is a directed graph? So we can have graph or network graph that looks like this, say 4 nodes. We know arrows, meaning that you can move from this node to this one and back with no problem. But in a directed graph, you have arrows, meaning that the flow is only in one direction. So that's what we talk about here. So the precedent diagram is a directed network, and it's often used in project planning. The precedence diagram shows part numbers on the arcs and denotes operations and inspections by circles and squares. So in the next diagram, showing one of those precedence diagram. Again, remember this is a directed graph, so you can only go in this direction until you get to the final product. Any questions?
Why doesn't that don't have arrows? Why does that have arrows in the graph?
Well, you don't have to show the arrows, but you need to know that it's a directed graph, meaning that the final assembly will require the components going in this direction. Any other questions? A good question. Okay. Okay, so the last thing that we're going to discuss today is schedule design. So we talk about product design, process design, and now schedule design. Any ideas of what we're going to be trying to do in the schedule design? When you hear the word schedule, what comes to mind? Yes.
Time frame for the product.
That could be one thing. Building the time frame for the product. What else? If I ask you, what's your schedule for this week? What are you going to tell me?
When you're going to class.
Exactly. So you go to class these times. If you're working, you go to work these times. So that's the type of decisions that we are going to be making now. How many units, at what time, how many machines are going to be used, and so on. So we're going to talk briefly about the schedule design. We're going to come back to these later in the semester. But we can start talking about how many units do you need to start producing if you want to get an output of 1,000 units by the end of the week. That type of thing. Okay? So schedule design provide answers to questions involving how much to produce and when to produce. Production quantity decisions are referred as lot size decisions. And determine when to produce is referred to as production scheduling. In addition to how much to produce and when to produce, it is important to know how long production will continue. And such a determination is obtained from market forecast. So if you're coming with the new cell phone design, let's say the iPhone 6, you want to know for how long are you going to be producing this new product, because you know that at some point you're going to come up with some new ideas and design a new product. So the production of such an item will not continue forever. So that's the type of decisions that you need to make, and you need some market information as well about the product. So specifications of process requirements typically occurs in 3 phases. The first phase determines the quantity of components that must be produced and includes allowances for defective items. Okay, so you don't want to send a defective item to the world. You want to make sure that you check find if you have a lot with multiple defective items, and you want to make sure that if you are guaranteeing 1,000 units to your customer, all those units are good units. So you have to take into account you will always have some defective items. You might be able to discard those, or you can fix those, and we're going to talk about that in a few minutes. The second phase determines the machine requirements. For each operation. And this second phase, we're going to discuss that one later in the semester. For now, we're going to focus only on the first one. And the third phase combines the operation requirements to obtain the overall machine requirements. So in this step, we look at specific operations. Here we're looking at the overall, or the final assembly, how many machines, how many units, and so on. So in terms of the first phase, quantity or the production requirements, taking into account the defective items. The calculation of production requirements. So we're going to look at what's the input in terms of your production or in your manufacturing line. How many units do you need at the beginning to end up with the required amount that you need to satisfy the requirements for your customer? So if you want to produce 1,000 units, you might need to start with as an input of 1,000 and 1,100 units, because 100 of them could be defective. So that's the idea. So we're going to use some notation here. DK represents the percentage of defective items produced in each one of the operations. OK is the desired output without defects, and IK is the production or the input for your production. Okay, so we can derive a expression to compute the input based on the output. So if you have an output required of 1,000 units, you can compute that output using the input minus the defective unit that you're going to have. Simple math. And you can solve for IK and get an expression in order to determine what will be the input required for your process. So this is actually the expression that you're going to use. So you're going to determine the input for your process using the output required and also the predicted number of defective units that you're going to have. And this is only for a single operation. So you say you have only one machine, you provide the input, you process the product, and you have an output. So this is the expression for a single operation. But as you know, most of the time you're going to have multiple operations in order to get that final component or product. So when that's the case, we can expand our expression to compute the input required in the first operation by looking at the output on that final production machine divided by, or multiplied in this case by 1 over 1 minus the defectives percentage for the first operation times 1 minus the defectives of the second operation, and so on. So I'm going to show you an example for this case. So one more time, ON is the required production volume for the final product. Okay, so here's the first example, calculating the production requirements for a serial process with 3 operations. So here we have 3 operations. We have information about the market estimate, so we need to produce 97,000 components for this run. So we have 3 processing steps: turning, milling, and drilling, and we have defective estimates of 0.4 for the first operation, 0.01 for the second one, and 0.03 for the third one. Okay, so I'm already giving you the answers here for this problem, but I want you to see in detail what's going on. So this is what we're trying to solve. I'm going to represent this using a network. We have one process, we have a second process, and we have a third process. So we're going to have an input for the first process, and we are trying to find out what that input is. And we have an output required based on market of 97,000 units. But after each operation, we know that we're going to have some defective units. So that will go out of the process. So we have defective 1. So by combining this and this, you can know what's going to be the input of the second operation. So we're going to have second input. We don't know what that is yet. But from here, we're going to have another set of units that are defective. And we're going to have a third input. We don't know what that is. But we know for sure that there's going to be some defective units also leaving that node. Okay, so what we are trying to find out is if we want to get this number of units at the end of the process, how many units should we start with? Or what should be the plan in terms of define first input? So in order to get to that number, we need to go backward and compute I3, I2, and finally I1. So we can compute I3 going back to this using this expression. So I3 is going to be equal to 97,000 divided by 1 minus the D3, which in this case is 0.03. And this equals 100,000 units. So I3 is 100,000. Now we can compute I2. So we know I3. So this should be 100 divided by 1 minus D2, and D2 is 0.01. So this equals 101,010, and that's going to be our I2. And finally, we can compute the initial input, I1, using the information from I2. So I1 is going to be equal to 101,010 divided by 1 minus D1, which is 0.04, and this is equal to 105,000 units. Which is that number. So as you can see, the table is giving you these results. You have 97,000 right here. Then you have 100 and 101. And then your final input is this amount. We can also compute this in a different way. So as I mentioned, when you have, if you consider each operation independently, you can use this expression. But if you want to consider them all together, you can use this expression and get the same result. So if we do that, we are gonna look at this. So I1 is going to be equal to 97,000 divided by 1 minus 0.03 times 1 minus 0.01 times 1 minus 0.04, and that should be equal to the same number. Okay, so two different ways of computing the same thing. In this example, we are not considering rework, meaning that we can use these effective units and repair them and bring them back to the next sequence. We're just taking into account the good units. We're going to talk about rework in the next lecture. Any questions? Okay, so that's all for today. If you haven't signed in the sign-up sheet, make sure that you do that before we leave. And I'll see you next Wednesday. And here's the attendance sheet.
For turning in that homework, we just need to have it to you by like 5 o'clock today? Or?
Yes.
Okay.
And you can print that right away. It will take you like 2 or 3 minutes.
Okay.
Yeah. It won't be something that you need to think about. There's information about yourself. Okay?
Thank you.
Mm.